So I wanted to go over your chapter review just a little bit, some questions here so that you'll have these for the test. Define energy. What is energy? Basically the energy, what did we say that was before? We said it was the ability to do work, right? In thermodynamics, what is the system and the surroundings? Well, the system is that portion of universe of our sample. It's like the system is going to be what we're studying, that sample of matter. And the surroundings are all the other parts of the universe. So number 3, does gasoline in a car's tank represent kinetic or potential energy? What would you say? Gas is potential energy because it's just sitting there, and gas can actually give us energy, right? So you'd say potential energy. What is a state function, and how does this concept relate to internal energy? The state function is determined by the state of matter defined by the temperature and pressure. So it has to do with the internal energy, right? So it relates to internal energy in that way, defined by not only the state but temperature. It's actually to have a relative position in that state. So in what direction does heat always flow? Well, you get that from hot to cold, right? So far the questions are pretty easy. You need to know all of these formulas too. It's kind of important that we know, especially this one. You probably need this one. This has to do with specific heat. And anyway, these formulas, last one we do with spontaneity, just to know what you're talking about. This is about energy. This one's about work, and heat and work have to do with energy. And this has to do with enthalpy, which is a type of measurement of heat, but it's includes energy and pressure and volume, usually in the midst of that, which we went over. And this is specific heat. And this goes on to what's lost and what's gained being equal. One's negative and the other one. And these products. So you have enthalpy being the products minus the reactants. We did that. And then, of course, spontaneity is that enthalpy minus temperature times entropy. But we went over those things. So anyway, so let's go on to the next here, see what other questions we have. So what is the specific heat of a substance, and how is quantity symbolized? So specific heat is the heat required to cause a unit rise in temperature, the specific heat. And some require little and some require more. So it's basically the specific heat for that certain substance to raise a unit and rise, such as temperature. So specific heat. So let's go on to, and how is the quantity symbolized? As a little c. This would be a little c, okay? A little c. So what is the purpose of a calorimeter? And the calorimeter is going to measure what? It's going to measure a device used to measure heat flow, right? So let's go on to number 9. The heat of a reaction. Why might this quality be important in such fields of power plant engineering? Well, the heat of reaction has to do with enthalpy, or it means basically that, to warm in. So that heat of reaction is very important. And to take volume and pressure, it usually takes volume and pressure. So when you have a power plant, you have to make sure, as for gases being let go, you have to take into account volume and pressure. So enthalpy will be very much more important than heat, because heat doesn't measure pressure and volume. Okay? Say, okay, what is the standard enthalpy of formation? The standard enthalpy of formation is basically that is the heat of the it's actually the heat of the products. The standard enthalpy is positive. It has a positive H, and products are colder when it's positive, right? When the enthalpy is positive, they're colder. And reactants, so reactants plus heat produce, the reactants plus heat on one side produce positive. We went over that. That's endothermic. So when we talk about endothermic, right? How does the quantity allow us to predict weather? So we can predict whether it's endothermic or exothermic, basically by the enthalpy produced, whether the reactants plus heat are going to equal positive or endothermic. If they're letting off heat, you know it's going to be negative. So distinguish between heat of fusion and heat of vaporization. Heat of fusion is what? Melting, right? And the heat of vaporization is turning to gas, right? So on to number 12. What is entropy? Entropy is disorder or randomness in a system. It's measuring how disorderly things become. And the second law of dynamics is that entropy of the universe is always increasing from order to disorder. So this whole section, just to know those things. So problems here, see if I can go over. I'm not going to go over any mathematical problems in this. We'll do those, you can do those on the test area or the samples, because I can't get my paper up here for you to see it very easily. So let's go over the problems. First problem is, for each of the following, determine whether the characteristics suggest an exothermic or endothermic process. So if something is absorbing heat, what's that's going to be? Endothermic, right? Because it makes it cooler. If you're absorbing heat, basically that on one side you're absorbing energy on one side, the other side is going to be cooler. So if you're absorbing heat, it's going to be endothermic. Now if you're giving off heat, it's going to be exothermic. So products are very cold to the touch. This is going to be endothermic, right? Because basically that heat's been taken out and absorbed in the reactant. So things are cold. Heat can be regarded as a product. Whenever heat is produced as a product and heat is exiting, you have an exothermic. If it's releasing energy, it's going to be exothermic. Okay? So let me see if I can go up a little bit so you can read. There we go. So let's go on to this question. Okay, this is a question basically having a sample at 100 degrees centigrade, 100 grams of water. The final temperature of the gold is water. So what is the specific heat of the gold? And to do this, I could work it out for you, but basically you're going to as using the temperature, you're going to use that form that's Q equals MC times the change in temperature. So you're going to have to fill this in. So I'm not going to do this right now. We'll do that one of those later on. The reaction between aluminum and iron oxide. And so you're going to calculate H for the reaction. Let's see. Did I do this one? I'm going to have a hard time showing this one to you, but it has to do with moles, and we'll have to use the table, so I'm not going to do that one right now either. So some of these I'm going to skip around for, see, number 3, number 5. Let's see, let's just go up to number 5, because this is another question I'm going to have to show you rather than tell you how to do. So question 5 says, tell whether each of the following increases or decreases in entropy, which is disorder of the system. So let's go through these. Evaporation from a puddle is going to go from order to disorder. Evaporation is always going to increase in entropy. So this would be an increase in entropy. B, the deterioration or the detonation of TED. You have TNT, this is a bomb going off. What do you have then? You're going to have an increase. So you want to have, whether it's increase in entropy, you're going to have a drastic increase in entropy, because it's basically going from order and blowing up into disorder, right? So this is going to be positive. What did I say? Positive? Okay, yes. Okay, number C, combustion of gasoline. That's another one, like a explosion. So that's going to be increase in entropy too. So the separation of air into its component gases. So air is going to be separated into component gases. What would you say? Air to gas increases the entropy, order to disorder. On to E, the construction of a building. Well, a building goes from disorder to order, right? You're building something. This is going to be a decrease in entropy because it's not being destroyed, it's being built up. The demolition of a building is going to be from order to disorder, right? Or it's going to be basically demolition. You're destroying the building. It's going to be an increase in entropy. The digestion of food is going to also be, it's breaking down food, right? So if you're breaking down food into simple things, you're going to be a positive, going to be an increase in entropy. The freezing of a lake. Well, the freezing of the lake is going to be opposite because it goes from liquid to solid. So this is going to be a decrease in entropy, okay? Just to know how some of these will be on your test, I'm sure. And this is another calculation here, so I can't really show this without showing you on my paper, because if I just tell you, it's going to be a little hard to explain. But we'll do these on the quizzes, because there'll be similar ones on the quiz as you do, and you can look back at your examples here. So let's go ahead and stop there. I don't think there's a thing going on at the next section, so let's stop.